When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were. Light travels at a finite speed. The farther away an object is, the longer its light takes to reach us. Some galaxies are so distant that their light has traveled for more than 13 billion years. That means we see them close to the beginning of the universe. But there is a problem. As the universe expands, light from distant galaxies stretches. Its wavelength increases. Visible light shifts into the infrared. To see the earliest galaxies, humanity needed a telescope that does not focus on visible light, but on infrared radiation. That requirement shaped everything about the James Webb Space Telescope. It was not built to take prettier pictures. It was built to detect the oldest light still traveling through space. Infrared telescopes face a challenge: heat. Anything warm emits infrared radiation, including the telescope itself. If the telescope is not extremely cold, it will glow in infrared and drown out the faint signals from distant galaxies. That is why JWST carries a massive sunshield, about the size of a tennis court. It blocks heat from the sun, earth, and moon. On the cold side of that shield, the telescope cools to below 50 Kelvin. Only at those temperatures can it detect ancient, faint infrared photons. Humanity did not just launch a telescope. It built a precision-cooled observatory and placed it 1.5 million kilometers from Earth at the Sun, Earth L2 point. Far enough to stay cold, close enough to communicate. Unlike previous telescopes, JWST was too large to launch fully assembled. Its mirror and sunshield had to fold. After launch, hundreds of deployment steps had to execute perfectly. Each mechanism was single-use. There was no repair mission possible at L2. Over several weeks, engineers watched as the telescope slowly unfolded in space. Sunshield layers tensioned. Mirror segments extended. Secondary mirror locked into place. Failure at any step would have ended the mission. Instead, deployment succeeded, and humanity gained the most powerful infrared observatory ever built. When the first deep-field image was released, it showed thousands of galaxies in a tiny patch of sky. Some appeared far older than expected. Webb began detecting massive galaxies forming earlier than cosmological models predicted. This did not overturn physics, but it forced refinement. JWST is not just confirming theory, it is testing it. By measuring galaxy formation, star birth, and atmospheric chemistry of exoplanets, it extends humanity's reach into both cosmic history and planetary science. For the first time, we are observing the transition from the universe's dark ages to its first light. And we are doing it with a telescope built to see what visible light can no longer show. When Webb observes a distant galaxy, it does more than capture an image. It measures redshift. As the universe expands, light stretches. The farther the galaxy, the greater the stretching. That stretching shifts light toward longer wavelengths, into the infrared. By measuring how much the light has shifted, astronomers calculate distance. And distance in cosmology equals time. A galaxy at redshift 10 is not just far away. It is seen as it existed when the universe was only a few hundred million years old. Webb's infrared sensitivity allows it to detect galaxies at redshifts never reached before. But detection alone is not enough. Webb uses spectroscopy, breaking light into its component wavelengths, to determine chemical composition, star formation rates, and ionization states. It does not simply photograph ancient galaxies. It analyzes them. Humanity is not guessing when the first galaxies formed. It is measuring their fingerprints. Early observations from Webb revealed something unexpected. Galaxies in the first few hundred million years appeared more massive and luminous than many models predicted. This did not mean cosmology was wrong, but it meant galaxy formation may have been more efficient than assumed. Webb's instruments, particularly NIRCam and NIRSpec, allowed astronomers to confirm that some candidate galaxies truly belonged to the early universe, not to closer, dust-obscured systems. By combining deep imaging and spectroscopy, Webb separated illusion from reality. Some early claims were revised downward after better data. Others were confirmed. The process demonstrated something essential. Webb is not rewriting the universe. It is refining the timeline. And it is doing so with precision rather than speculation. Infrared light has another advantage. It passes through dust. Many regions in the universe, especially star-forming regions, are hidden in visible light by thick clouds of gas and dust. Webb's infrared sensitivity allows astronomers to look inside these clouds and observe star formation directly. This capability applies not only to distant galaxies, but also to nearby stellar nurseries. Webb has revealed structures in star-forming regions with unprecedented clarity. Protostars, jets of material, collapsing gas clouds, all visible through wavelengths invisible to the human eye. This connects early universe cosmology to present-day star formation. The processes shaping galaxies today are linked to the ones Webb observes at cosmic dawn. Infrared is not just about distance. It is about penetration. Although built to study the early universe, Webb also examines exoplanets. When a planet passes in front of its host star, a small fraction of starlight filters through its atmosphere. Webb measures this filtered light. From tiny absorption features in the infrared spectrum, scientists identify molecules such as water vapor, carbon dioxide, and methane. This technique does not prove life, but it measures atmospheric chemistry with unprecedented precision. In some cases, Webb has detected carbon dioxide in exoplanet atmospheres for the first time. This expands humanity and cosmos beyond structure formation. Webb is not only looking back in time. It is analyzing environments where life might someday be possible. The same telescope that studies the first galaxies also studies distant planetary atmospheres. The scale is different. The method is the same. Measure the light. Extract the physics. Before Webb, the earliest confirmed galaxies were detected by the Hubble Space Telescope. Hubble pushed back the timeline of galaxy formation to within about 400 to 500 million years after the Big Bang. Webb extended that boundary further. By detecting galaxies at higher redshifts, Webb revealed that structure formation may have begun earlier than many models predicted. But the shift was not dramatic chaos. It was refinement. Some early galaxy candidates initially appeared extraordinarily massive. Later spectroscopic follow-up clarified that some were less extreme than first thought. This is how cosmology progresses. Webb does not overturn the Big Bang model. It narrows the uncertainty window around when the first galaxies assembled and how quickly they grew. The early universe is no longer a theoretical sketch. It is becoming a measured epoch. Large-scale structure formation depends heavily on dark matter. In cosmological simulations, dark matter collapses first, forming gravitational wells. Ordinary matter falls into those wells and forms stars and galaxies. Webb's observations allow scientists to test whether this sequence matches reality. If early galaxies formed too quickly or were too massive, it could indicate that our understanding of dark matter behavior needs adjustment. So far, Webb's data are broadly consistent with the standard cosmological model, known as lambda CDM, but it is testing it at higher precision. Webb provides constraints on how fast matter clustered and how luminous early systems were. This does not mean dark matter is solved, but it means cosmology now has sharper tools. Humanity is not replacing models. It is stress testing them. After the Big Bang, the universe cooled and entered a period known as the Cosmic Dark Ages. No stars had formed yet. Eventually, the first stars ignited and began emitting ultraviolet light. That radiation ionized neutral hydrogen gas, making the universe transparent to light. This era is called reionization. Webb is now directly observing galaxies that likely contributed to this transformation. By measuring their ultraviolet output, shifted into infrared, scientists estimate how much ionizing radiation early galaxies produced. This helps answer a fundamental question. What ended the Dark Ages? Before Webb, this period was inferred indirectly. Now it is being observed in detail. Humanity is no longer guessing how the first light reshaped the universe. It is measuring the sources responsible. Webb has not broken cosmology. It has strengthened it by forcing more precise questions. Are star formation rates consistent across environments? Did galaxies assemble through rapid mergers or gradual growth? How do black holes form so early in cosmic history? Webb provides data detailed enough to challenge assumptions, and it will continue doing so for years. Its instruments are still in early operational phases. Surveys are ongoing. Follow-up observations refine earlier findings. What Webb represents is not a single discovery. It represents an upgrade in measurement capability. Humanity now observes the universe with higher sensitivity, greater resolution, and deeper reach into time. The earliest chapters of cosmic history are no longer beyond reach. They are part of the observable record, and they are being measured.